and don't, and it needs to be single column, so 11 point or larger font. Okay, let's see if I can extend this over, but like, let's touch highlighting isn't working, but okay, so this is important. Don't squeeze it down too far, okay? I'll need to read all these. If I'm squinting, I'm not going to be happy, and the grade's not going to be as good. Okay, and so and so you can reuse sections from your proposal or your data collection report or the intermediate report. So that's fine, right? So don't be intimidated by the 12 pages. You've probably written close to half of it already, okay? But there should be new material, and I've got this part here about if you work in a group, make it clear who worked on what. But I'd rather it be one long narrative for the project, okay? So don't write so-and-so did this, so-and-so did that, and so and so on. Like you can just make a note someplace, mostly who did what. In most cases, everyone in the group is going to get the same grade. If there are big differences in what people did and it seemed like someone wasn't carrying weight, I occasionally have different grades for different people in the group. But that's actually hard to do in Canvas the way it's set up. So most people will get the same grade, right? But so make it one narrative. Okay, I don't want to have to read 3 separate projects stuck together. Okay, so try and make it one narrative. Other things, make sure you have a title and name on it. The title is important because you're going to be making posters for this, and we'll discuss the posters more like in a week or so. But you'll have the same title on your posters. Okay, so don't make it too long. Make it under 10 words probably. Okay, like 3 to 4 words is usually a good number. Sometimes a little longer is fine. And then like in addition to like what is the problem, motivation, and what is the data you explored, which is from your other reports, I'm interested in what interesting thing did you do. I like to kind of learn a little something when I'm reading these reports. Okay, so try and bring out a key idea, something you explored, something that was new. If I learn something new, I'll be very happy. Okay, so most of the grading so far, and also will be roughly the same in the posters, and we'll discuss that more, but has been basically if you followed the rules, you're going to get all the points. If you go over the page limit, you're going to lose points, something like that. But in this one, I'm going to have some leeway. Okay, so it's out of 50 out of the 100 total points of the project, 50 are on the final report. And I have some leeway between 40 and 50 points. Okay, so think of an average project will be 45 points if they follow all the rules. One that was below average and satisfied all the requirements might get 40, and one that's truly outstanding could get all 50 points. All right, so like an average one will get 45, and that should not, and that like, you know, out of your total grade, that's like drops 2.5%, right? So this might change grade boundaries just a little bit, but this is not going to be preventing you from getting an A, right? Even if you do an average report here, okay? But I'll have some leeway there, but you know, if you follow the rules, all the requirements, you'll get like at least 40 points, so you'll do fine. And now, if you follow all the rules, that's 90 out of 100 points on the overall project. All right. So, any questions about the reports? Or doing a week? Yep. Okay. Feel free to ask me after class again on Wednesday. You know, in office hours over email. Happy to help with this. Okay. So Markov chains. Right, so again, so who's heard of Markov chain before? And who's not heard of a Markov chain? All right, so a few of you haven't heard of it, but and a number of you didn't raise your hand, so I'm guessing maybe you've heard of it but are not familiar with it, or you have arm injuries, possibly. So I shouldn't have discriminated. You could have raised a leg, that would have been fine. Okay, so this lecture will kind of be a lot of just definitions of what are Markov chains. But these are important, right? And the reason we're describing Markov chains is they're kind of the foundation for a lot of understanding about how to think about graphs. And it's related to kind of the eigenvector value view that we saw for spectral clustering, and we'll see this relation, but it gives kind of an orthogonal view of how to think about these large graphs. So to try and I'm going to go over the definitions of what specific type of Markov chain that ultimately is going to be called ergodic. There's no R there. Ergodic. And if a Markov chain is ergodic, then there's a lot of nice things, powerful things you can say about it to use for analysis. But you have to understand what makes up this property. So kind of go through the definitions. To mix it up, I've kind of like to add three life lessons that you can learn from understanding these Markov chains. So only your current position matters. So in life, I guess. So as you're going forward, so don't worry about the past. Okay. And so for those of you who know Markov chains, maybe you'll guess where these are going to come from. So you just need to worry about taking one step at a time, and you will get there eventually, or maybe you won't, right? And again, for those of you who know, you might be able to guess where this is coming. If not, you'll see a mathematical rationale for these, and then also in the limit, everyone has perfect karma. Okay, so if any of you have guesses, kind of make them internally now and see if you can see where these come up. Okay, does anyone think they know where all three of them, what property Markov chains are going to correspond with? Yeah? Okay, cool. All right, we'll see if they match. Okay, good. All right, so Markov chains are often, but not always, fundamentally about graphs. And we'll talk about cases when they're not, like in a lot of Bayesian inference. You can kind of think about them like graphs then too, but we'll kind of get to this. But this is the graph section of class, right? So again, I showed a slide picture example like this before. We were talking about spectral clustering. And again, so we have a graph that's defined by these vertices, A, B, C, D, up through H, and these edges between the vertices. Okay, and then there's this matrix-style representation of the graph that, ones and zeros. There's a 1 if there's an edge between A and B. Okay, and so you can write this as this matrix here. Okay, and typically this is an inefficient way to represent it because it's going to often for graphs these are mainly zeros. Right, so if you store all the zeros, you're storing a lot more than this representation. But mathematically, this will be very powerful. This was the adjacency matrix when we looked at the spectral clustering, right? So in Markov chains, we want to do something slightly different, and we could have directed edges, but we'll see it. What's going on here? And so we're going to change this adjacency matrix slightly to this probability transition matrix P. Okay? If we go back and forth, we look at the first column here, 0, 1, 1, 1, 1, 0, 0, 0, 0. What did we do? We took the column and we normalized it in the way so that they summed up, all the entries summed up to 1. So if there are 3 of the entries, I divide them each by 3. In this column, there are 2 entries, I divide them each by 2. And This one only had one entry, so I divide by 1. It didn't do anything. I could have divided, if there were 8 edges off of a vertice, I'd divide by 8. You want all 1/8 here. Okay, and so you can have this more general, but this is the standard way to convert a graph into a probability transition matrix. And then a Markov chain is defined by 3 components here. The node set, which is the node set of your graph in this case. The probability transition matrix, which can be defined like this, or you could define it in other ways as well. I could put other probabilities on, I could think of each column now as a probability, and I'll explain what this means in a second, but as long as they're all greater than 0, greater or equal than 0 each entry, and they add up to 1 in each column, this satisfies. And then the third thing I need, the third part is this initial state. Okay, and I can represent this a couple ways. Either in this first representation, it's got one entry for each of the vertices in the graph. Okay, so the first one, the one here in green, this one I can think of as a vector. That's why it's Q transpose. But it's this vector, what has a 1 in the state corresponding with B, right? And has 0 everywhere else. So that means this is describe a probability distribution over where I'm located, and says I'm definitely, with probability 1 located in state B, probably 0 located in all the other states. You could also think of a representation of a state like this, where now I have this corresponding to A, this B, C, D, E, F, and this F. So that means I have 1 out of 10, I'm in A. 3 out of 10, I'm in D. And 6 out of 10, I'm in F. So it's kind of a probability distribution of what state and what vertex in the graph I'm starting in. And so to define a Markov chain, you need these three components. Okay, in the general case. And in some cases, if the Markov chain is going to be ergodic, then I'm not really going to need this Q state. I won't necessarily need the Q state. Okay, so and if I don't need the Q state, then I really only need the graph, right? Because then the graph will tell me the vertex set, and the edges will tell me this I can convert this into this probability transition matrix. Okay? And if I had a weighted graph or I had a directed graph, I could convert it similarly into a probability transition matrix. Right? So let's say I'm at A, right? And A has 3 edges going to C, to D, and to B, and these correspond to these 3 entries here. Let's say that these have a weight of 1, 1, and 2. So I'd say I'm twice as likely to go to move from A to B as I am to go to C or D. Right? So then what I would do is I would replace this one with 1/2, this one with 1/4, and this one with 1/4 inside of this state matrix. Okay, so if I had weights, I would just add up the weights and divide those by the sum, and I would normalize them this way. I could do that with weighted matrices as well. In this case, it's symmetric based on the edges, but not necessarily the probabilities. Right? So if I look at, let me do it someplace else. Let's look at between at this edge between E and F. Right? So A, B, C, D. This is E, and this is F. This is E, and this is F. Oh, those are the same. Let's look at between, let's see, F and G. F and G. So what these are capturing is saying I'm in state F, and the probability I transition to another state, in this case the probability I'm going to transition to state G, is going to be determined by this probability right here. Right? So if I'm at this location F, and I'm going to go to one of the three neighbors. In this case, I'm equally likely to go to each of them, E, G, or H. I could go to one of these two, of these three. Okay, and so I have 1/3 probability of walking to each of them. Yeah?
Yeah, so the column is where you're starting from, and the row is where you're going to?
Yes, that's right.
So should that go 1/2, 1/4, 1/4 in the pink marker then?
Oh yeah, to go to B is twice as much. Yeah, I messed those up.
Okay.
Thank you. Let me fix that. Great. Thank you. Good. So at least one person's paying attention. So great. Okay. Good. Right. So these don't need to be the same, right? This is the probability I'm in F and I'm going to G, and this is the probability I'm in G and I'm going to F. Right? The probability of going from G and going back this other direction, I can only go to E or to F, but I can't go to H here. I don't have an edge, so I have 1/2 probability of getting back to F once I got to G. Right? So these don't have to be equal, even though in the adjacency matrix these were equal. Right? And it kind of means I can change them, and it's still a valid probability transition matrix as long as each of the columns adds up to 1 and all the elements are at least 0. Right? They're all probabilities, and each column is a probability distribution. Okay? So again, how many people have seen this formulation before of a Markov chain? This is kind of familiar view. Okay, I know there are other views. We'll get to these other views as well. Okay. So then the cool thing about the Markov chain, and the reason you set it up this way with these states Q, right? Remember, this is a state, and this is the probability transitions, is because if I'm at a particular state, let's say I'm at state B, probability 1, and I want to know where I'm going to be after the next step, all I need to do is multiply by this matrix, P, right? And this gives me a new state, Q1, right? And its representation is where the probability distribution of where I'm going to be. I could have only moved to state A or D, and each of them are equally likely in this case. Right? And even cooler, you want to go 2 states, right? So I multiply by this matrix twice. Or I can take the state Q1, right? So this is multiply twice. This one, I do Q1 where the probability distribution of where I was after one state, and I do it again, and this is the equivalent. Or I can create this matrix P squared, where I take P and I multiply it by itself, and this takes from any initial state, and I multiply it by this P squared matrix, and that tells me where I am after 2 steps. Right? So these are all equivalent because of kind of the linearity of these linear algebraic operations. Yeah.
Can you explain what is Q2 doing? I mean, what does it mean?
So Q2, this is a probability state vector, and this means that if I start in this initial state, Q up top there, which is in B, and I make 2 steps, then the probability distribution of where I will be is 1/6 of the time I'll be in A, 2/6 in B, back in B, 2/6 in C, and 1/6 in D, and I will not be in E, F, G, or H. Right? And if I look back at the picture of the graph, a clean picture of it, if I'm in B, I cannot get over to E or beyond after 2 steps. Right? If I start here, there's no way I can get to E after 2 steps. Right? And I can get to somewhere else and I can go back to B again. Right? So that's allowed, but I can't make it out to E or anywhere beyond there. If on the other hand, I take 3 steps, then I can make it out to E. Right? Which would have meant I had to make it to state D and then I take one more step, and 1/3 of the time I make it out to E. Right, and so, and this captures this probability distribution of where I would be after 3 steps or after 4 steps, and so this depends on the initial state. Right, if I started in H, then I'm going to have more mass, probably mass on this side of the function, and less on this side.
I'm sorry, what do you mention about moving forward or backwards? It includes both ways, or?
It always thinks of going forward. Sometimes you get back to the state that you started at, but you always think of moving forward. Yeah.
So the further out you try to predict what state you'll be in, Q1 to Q infinity, the more uncertainty you'll have in being able to predict any single state arrival.
Maybe it's going to be more diffuse, at least initially. But there'll be other things we can say. Sometimes you'll be even more sure about it in the limit. And I'll go through some examples.
Do steady state vectors also exist in this context?
Sometimes, and we'll talk about this. This is where we get into next, right? Okay, so in the limit, you can take n as n goes to infinity. After n steps, q times p to the n is the state qn. And we'd like to refer to something that's q star, which would be some nice limiting distribution about this. You cannot always do this. You cannot always think about this limit. This is not always well behaved, and if it's not well behaved, then it's hard to use this sort of analysis. Okay, so I mentioned there'd be lots of definitions, so there'll be more definitions that will tell us when this is well behaved, when can we use this analysis about understanding this limit, which would tell us about when can we understand what's going to happen after many states, and all sorts of stuff. And this is so if the Markov chain is going to be ergodic, this term, then it means that we're going to have this limiting state. And then we can study that state and nice properties about it. Okay, good. So far, just the mechanism is clear enough. And it looks like these finite state automata and all this stuff that you probably study if you're CS majors in 2100, I guess, right? So it should look familiar to all of this sort of stuff. You may not have used linear algebra to do that, right? Okay, so again, so this is life lesson number 1. Only your current position matters going forward. Don't worry about the past. We can always think about kind of moving forward in this process, always iterating forward. And so only the current position matters is what's known as like a Markov assumption. That I don't need to store information about my past. I can compute Q3 only from P2 and the rules of the game. P is the rules of the game. Where I was after 2 steps, well, one more step, I just apply the rules of the game. It didn't matter how I got here. It didn't matter what Q1 was or Q was after I got to that state. And so Markov was, I believe, a Russian mathematician. Maybe I have in my notes someplace. So Andrei Markov, which I believe is okay, so there are other Markovs in the family of the Markov family who do other cool stuff in math. There's a lot of stuff named after him where the idea is that I can ignore the state prior to the state I'm in now. I don't need to worry about the history of the process, only the current state in order to get the next one.
This is a linear algebra question. Is p to the power n defined as p multiplied by pn minus 1, or is it pn minus 1 times p?
Yeah, so p to the n equals p times p to the n minus 1 is equal p to the n minus 1 times p is also equal to p times p. This is n times. Right, right? And the order of operations isn't going to matter here because it's P on both sides.
Okay, thank you.
Right. I can collapse them in the middle and all that. Right. So if I want to, if n is the power of 2, I can do this. I can use like a binary thing to kind of do that. So I can pre-compute all the p squareds and make p to the 4ths and p to the 8ths. It might be a little more efficient. You typically don't do that. You typically don't actually compute that.
Okay.
But for analysis, it's useful. Okay. Okay. So this is the typical setup for Markov chains, at least from a graph point of view. And there are two ways to think about Markov chains, at least two different computational kind of ways of thinking about it. The mathematics are a little bit different, but they're roughly the same phenomenon. Okay, so let's say 1 is a random walk. Okay, so that you think of starting in, say, state B, and I have a graph, and I randomly walk to the next state, to state A, and then I walk to state D, and then maybe to state E, and so forth, right? And so so Q is always 0, 0, 1, 0, 0, right? It always has some deterministic one location, right? The state vector at any given point is always exactly one location in the graph. That's where I am. There's a probability distribution. You know, if I know where I am, that's where I am. Like if I'm a person jumping around a graph, right, then I'm always exactly in one state, right? And the probability transition matrix tells me about where am I going to be is a few states in the future. But then when I go execute that, I'm always going to be in one of these states. So exactly on one so vertex, okay? And so the other way of thinking about it is the probability so distribution. So Q can be dense. Okay, so this Q state vector can be dense. I can always be kind of moving, I can always be thinking of where I'm going to be. I don't ever have to realize my actual position. So now, I mean, these are really kind of the same thing, but you can think of computationally that you can do these different. One, if I do this, I only need to I only maintain you know, one state. I only maintain the exact location of each state as I'm hopping through. You can think of it so I can think of it like a finite automata, and I'm hopping through the graph. There's a control sequence for my program, and I'm moving through the graph in this way. Okay, and in this way, I can actually maintain a dense vector Q. Okay, so if I go through, I can do this where I do some vector Q times P over and over again. So if I show these pictures here, where I'm maintaining actually this actual dense vector Q here, which is going to look like this every step, right? Maybe I represent it as a double, so I get kind of, you know, a little bit imprecise. Usually you can't do it as these fractions eventually, but so I have some representation of it as like a double. Okay, and so this allows me to capture more information, the full probability distribution, as I'm going through this. The problem with this one is that if the state space is really large, then this isn't feasible. If the state space is super large, right? So if there are n states, then 2 takes O of n space, where 1 takes O of log n space. Okay, so I can think of it this way, where from like a computational, so theoretic view, I just need to store the index of the state I'm in here. So it's exponentially less space to store as I'm keeping track of this. And then you often would keep like a distribution of all the states you've been to. So you need to keep a distribution, but that might be much smaller than any one dense vector of this. The other thing is that n may not even be something that's finite. I mean, you could think of this as like all IP addresses, so it's like super huge. I'm hopping around all the IP addresses in the web. I'm a packet going as I may in some random process. But you can also think of this in a probabilistic modeling point of view. If you're doing computational Bayesian statistics, you often need to run a Markov chain of the first type, where you can't even, the state space is actually something that's continuous. You can't write down a graph. You can only define it implicitly. And so you can't even write down this vector. You can only say a current state that you're in at that time. Okay, and so we're going to come back to this and talk about a specific algorithm called the so-called the Metropolis algorithm that does this random walk point of view, which is kind of very related to what you do in Bayesian statistics, but was actually developed for problems in computational physics, and I'll explain that. I'll come back to this. To understand graphs, as we are kind of talking about now, this way is more useful. Often the graphs are large but finite, and I'm okay representing this much space. Okay, so I'm going to think about this second point of view for the next part of the lecture, and then we'll come back to the first point. Okay, so of those of you who raised your hand, said you'd heard of Markov chains, who had typically thought of them in the first way view, the random walk version of it? A couple, 3, 4, and who had more thought of it in the probability distribution point of view? Okay, so a bit more on the second type. Okay, but it's kind of split, and this is what I've found. Most people have heard one version or the other, and often, so not both views. But computationally, they're kind of different in how you work with them. Okay, so it's kind of clear. We'll see some examples of both as we go through more. But they both will both want them, in both cases, we'll want them to be ergodic, and then we can understand them using some nice mathematical formalisms. Yeah.
When you say ergodic, do you mean steady state vector?
What?
When you say ergodic, does that
an ergodic is a condition under which there's going to be a well-defined so steady state vector. So we'll see. I'll explain this more clearly. All right. So okay. So in order to define when a Markov chain is ergodic, which means it's going to have this steady state vector, it's easier to define actually when it's not going to be ergodic. Okay, and then I can rule out the cases when it's not ergodic and everything else is going to be ergodic. Okay, so there are 3 cases, and we'll go through them with examples when it's so when a Markov chain is not going to be ergodic, and I'll go through them by just writing down the probability transition matrices of the accompanying graphs. Okay, and we'll. Right, so the first one is a definition called cyclic, okay, and it means that the Markov chain is going to alternate between states, okay, and it's going to have at a fixed kind of epoch of size p. right? And so P is something that's going to be greater or equal than 2. Okay, so the first Markov chain is going to have two states, A and B. And if it's at A, it always moves to B. And if it's at B, it always moves to A. Okay, so it's never going to converge to A or B or a probability distribution of either of them. If it starts at A in the 0th state, then it's always an A on the even state, and it's always in B in an odd state. Right, an odd step number, right? So I can't think of this in the, when I try and think about the limit, mathematically I can't do it because it's not converging to anything. So it doesn't have this nice property of convergence. And it doesn't just have to have two states. In this case, I've got A, B, and C. Okay, and so what's going to happen here is that A is always moving to C, C is always moving to B, and B is always moving to A. Right, so I now have a cycle of length 3. And if I started in state B, then in every state that's a multiple of 3 minus 1, like 0, in every state that's a multiple of 3, 0, 3, 6, 9, I'm always going to be in B. Multiple of 3 plus 1, I'm always in A. Multiple of 3 minus 1, I'm always in C. Right, so I'm not getting this convergence behavior. And it can be more complex like this as well. So what is going on here? Basically, I'm going to have two states, A and A, B, and then I'm going to have B, C, D, E, and F. Okay, and basically everything from A is going to equally go to these states. F is going to go this way, and then they're going to go back. So, so I'm going to have what's known as a bipartite graph, where I can divide the graph into two sets of vertices, and there are no edges between the vertices in any of the halves, right? There are no internal edges on this half or in this half, so it alternates which half it's on. So again, it's a more complicated cyclic example here. Okay, so if it has one of these regular patterns where it's always at a certain state on some multiple of P, right, then I'm not going to be able to get some convergence analysis here. Okay? And all of these will be important when we talk about PageRank, which we'll talk about next lecture on Wednesday, which is like gave birth to Google. You need to understand all these issues. Okay. The second kind of bad category is when you have these absorbing and these transient states. Okay, and these absorbing and transient states. So absorbing is a set of states that you can never leave, and the transient states are set of states that if you leave, you can't go so back, right? So if I'm not sure if I did this right, but if you remember, like the matrix, there's the red pill and there's the blue pill, right? If you take the red pill, you're gonna go into the not into the matrix. I guess. Hope I didn't ruin this for anyone. Should be safe now, I think. If you're blue, then you stay in you live inside the matrix. Maybe you can get out again, but right? But like but you can't ever go back, right? Okay, so like in this example here, let's say I have A and I have B. Okay, and so if I'm in A, I can sometimes stay in A with probably 1/2, and sometimes I go to B, and if I'm in B, I stay in B, right? So I'm just going to keep coming back to myself. I have these self edges. Okay, so if I stay in A, I might stay in A forever, but every chance I could leak out to B, and once I'm in B, I can't ever get back to A. So A is going to be transient, and B is going to be absorbing. Okay? Let's see, what's going on with this example here? I've got A, B, and C. Okay, so if I'm in A, I always go to B. If I'm in B, I always go to A. This part seems okay. But if I'm in C, I'm always going to B. Right, so now A and B are absorbing, and C is going to be so transient. C, I'm always going to leave C, right? So I don't stay there very long. Once I get them, I don't have to stay in one particular state. I could be in a set of states, right? So basically, this set is going to be absorbing, and this set is going to be transient. Okay, and then I've got a more complicated example going on down here, where I've got, this is A and B. You can see there's some stuff going on here where this part is transient because there's one part that leaks and goes to the set of states that are C, D, E, and F. Right? Once I'm in C, D, E, and F, I'm kind of in this steady state among them. These are so absorbing here. Okay, and so there's this 1 out of 100 chance I'm in B, I leak out into this absorbing state, but eventually all of the probability will leak out here. Okay? So, so just a quick clarification. So I don't think I defined precisely cyclic so well enough. This was the other problem, cyclic examples. These are technically not cyclic. It depends on the initial state. If my initial state is in C, D, E, and F, my initial probability distribution is in here, and it's at one of these locations, then it's going to be cyclic. If it starts at A or B, it's not going to be cyclic. How does that work? Is it, I'm going to have other issues in that it's have these absorbing and transient states, which is going to break it. But I'm not going to have, my probability distribution will actually be fairly evenly spread out over these. It will depend on my initial states, what the probability distribution will be. It will slowly leak out, and some of it will end up being C. Oh yeah, and this doesn't have a cyclic. It's fully connected. But even in this second example, depending how much I start in C will depend how much is on A and B. The A and B part is kind of cyclic by itself, but because I have the C part on there, it kind of disrupts the cycle. So you can have a cycle, but you can have a small extra loop in there, and that can break the cycle, and it eventually lets the math spread to all these other categories. Okay, so the absorbing and transient, this also doesn't have the ergodic behavior. I need to know what the initial state is to tell me how it's going to wind up. You could also have an example where you have A, and I have B and C, and these go back and forth, and I have a state D here, and this has a self loop. And so, this could be 1/3, 2/3. So if I start in A, I don't even know what I could have two different absorbing states, and some of the mass could go down here, some could go down here, but that's even probabilistic, right? So there are different sorts of issues that come up in this case. So these are states which are types of Markov chains which are not easy to analyze, and I can't guarantee something about the limit. Or I can guarantee it'll be in the absorbing states, but I don't even know necessarily which absorbing states. Okay. And then finally there are these examples which are also bad, which which are where the graphs are like not connected. So this is A and B, and A always loops to itself, B always loops to itself. Right? So if I have some mass in A, it will never get over to B. Right? And this is one where A and B will go back and forth to each other, but C will loop back to itself. Right? And then this is a more complicated example with three different components. Okay, and so these indicate that it depends again on the starting state where the probability distribution will go. It might be cyclic within one of the components, but it depends where my initial mass starts. So if I want to use this to analyze graphs without knowing what this initial state is, these are kind of no good, because the converge to limit depends on this initial state. Yeah?
So when I've seen Markov chains, it was like to analyze or predict like where the best place is on the Monopoly board to play.
Okay.
Like modeled it with the Markov chain, but that just seems like one big cycle to me, because like the Monopoly board just goes around and around. So does that mean that there's some cycles that do allow you to analyze it, or does it, because you know like the starting state, that you can analyze that with Markov chains?
Yeah, so Monopoly board is actually fine, okay? And the reason why is that every time you roll, I forget if it's 1 or 2 die, it's been a long time, but you move between, so if it's like 2 die, right, then you move between 2 and 12 spots each time, right? So you're kind of mixing this across. If I always move 1 spot, or if I always move 2 spots, then there's some states I would, or maybe I always move 3 spots, so I could get to any state, but there's a fixed ordering I would go to them in, right? So that would be less interesting. But because it's random, and the 2 die, it's more concentrated around moving about 6 or 7 spaces, then I tend to move that much every step, right? So, but there's a probability distribution. It kind of smears out over time. Sometimes I'll roll a bunch of 12s in a row and I move really fast. Other times I'll roll a bunch of 2s in a row. So that's not quite this cyclic behavior, is where there's a very regular pattern. And this is a difference, and this is a specific sort of issue that comes up. But so in Monopoly, in most board games, this is fine. Yeah, and I think game makers will analyze the Markov chains of their games to understand kind of the distribution of where the states are. I think most modern games that would be a good way to do it. When they built Monopoly, do you know how old is it? Is it like pre-1950s? Yeah. It could be. So this is before people really knew about Markov chains, but we had an example in Monopoly, for instance. Yeah.
1935.
1935. Okay, so we'll.
According to Google.
Yeah, when were Markov chains? They're probably earlier than that. Markov was around the turn of the century, I think. So I don't know if Hasbro or whoever invented Markov or whoever invented Monopoly was aware of it back then, but you know. Okay, good. Okay, so now we can say that a Markov chain is ergodic if it is not cyclic, having, so 1 cyclic, 2 having absorbing and transient states, and 3 is connected. Okay, so if it doesn't fall into one of those 3 categories, and those are the only 3 things you need to worry about, then it's going to be ergodic, and that means that we can talk about this limiting state. Okay, so we can talk about this P star matrix will be well defined. Okay, the P star would be well defined anyways, but we're going to have this Q star vector. right? Where I'm gonna, independent of whatever my initial state is, I'm always gonna get Q star. This is going to be independent of Q. That means for any initial Q, the Q star matrix is going to be the state, or the Q star vector is going to be the state. Yeah.
For the third statement, should it be unconnected instead of?
It's ergodic if it is, yeah, if it's not unconnected. Okay, so, yeah. So there's a double negative there, but that's correct. Great. So if it's not unconnected, if it's not having absorbing in transient states, and if it's not cyclic, then it's going to be ergodic, and we're going to be able to say that independent of the initial Q or any or for any initial Q, I can multiply the initial Q by P star, and I'm going to get the same Q star, the same limiting state. Okay. Okay, and so again so the second life lesson, you only need to worry about one step at a time, so you'll get there eventually, right? So if life is ergodic, then you just need to worry about one step at a time, and you'll wind up probabilistically in the same state. Or if life is not ergodic, then you won't, right? And probably life has absorbing and so in transient states. But maybe certain aspects of it don't. I'll leave that up to your own thinking after class. Okay. So there's another nice property that this implies, which is called the delicate balance. Okay, and this just kind of gives you one of the nice things that is coming out of here, and that's that. Because P star is the limit as n goes to infinity, I can multiply this by another matrix P, right? So I can multiply this state, which is the same as Q star, and I can multiply it by P, and I'm going to get back Q star again. All right, so once I'm in this limiting state, because Q star is an example of some initial condition, I can multiply it by P again, I must get back Q star. Okay, so as I'm transitioning at this point, my probability distribution is fixed. It's limiting. This is one way to think about this limiting state. And one implication of this is in this limiting state, if I start in state I look at the probability of being in state I and transitioning to state J. That's going to be equal to the probability of being in state J and transitioning to state I. So I'm exchanging every pair of states which are connected, or if they're not connected, this would be 0. But every pair of states which are connected, I'm essentially, the amount of mass I'm transferring back and forth between them is equal, right? I can have some state I and some state J, right? And I have some probability mass going back and forth every step, and there's lots of other stuff going on here in this Markov chain, right? There's lots of other stuff going on where the mass is kind of spreading out, but between every pair of states, I'm kind of an equal amount of stuff going back and forth. So think of it like there's water flowing through a bunch of pipes, and they're in a stable state. Then maybe some's going back and forth, but it's not mixing. Or think of it as your water's flowing in some ponds at different levels of uneven heights. Maybe there's fish flowing back and forth, but they're roughly in this nice balance. So every pair of ponds is getting the same number of fish going back and forth every year. So the number of fish is the probability of being in that state, and the probability a fish moves from one to the other is kind of the probability of transition. I take the product of those, that's roughly the same. That's going to be the same in this limiting state. Okay, so this is just one kind of cool thing that happens. Okay, so in the limit, everyone has perfect karma. You know, it's kind of what's going on here. Okay. Yeah.
So Markov chains are like I read somewhere they're using predictive text. So far, from what I've seen, I don't see how it's probably being applied in like predictive text.
Okay, so there's a bunch of related concepts that if you take an AI class or like a natural language processing class, you're going to get things like there are these other or like in imaging there are these things like Markov random fields. There are these so what am I thinking of? There's what's the object that like the Viterbi algorithm is run on top of. These are slightly different concepts. They're all named after the same Markov in that you can look at one state at a time. But they're slightly different in some regard. So there's like a Markov decision process where you're making observation and then you're taking an action every step. But you're defining this over a big state space similarly, but you're seeing how actions influence you. And this is a different sort of process that's more complicated. Again, Markov chain is the basis of this. If there are no observations, then you're in a Markov chain. If there are observations, you're in something more complicated. Okay. What else do I want to mention? Yeah, so the other thing about this is how Q star relates to P. So Q star, it turns out it's the first eigenvector of P. Okay, so if I do the Eigen Decomposition of P, then the first eigenvector is going to be exactly Q star if the matrix is ergodic. If it's not ergodic, there's some other weird stuff that can happen. Right, so one proof of this, if you've seen the power method for computing the eigenvectors, that's basically exactly like running the Markov chain forward. Right, so I think it's in the notes somewhere, but I didn't describe it in class for time, but how to compute the eigenvectors, you take any given initial vector, usually you take a Gaussian random vector, and you multiply it by the matrix over and over again, and this gets you the first eigenvector. Right? So one way of doing this, and again, this is built into MATLAB, and this will have to do with your homework. You can run I of P in MATLAB. This is MATLAB, or okay. You guys notice that? Okay, so if you run this in MATLAB, this I command, it'll give you the eigenvectors and the eigenvalues. These are the eigenvectors, and these are the values. And so so you can just read these off, and the first eigenvector is going to be Q star. So then V1 is going to be Q star. Okay, the other useful thing about this is the second eigenvalue, lambda 2. Okay, so typically what you do to analyze this is and these the other note is these eigenvectors are not normalized the right way. These eigenvectors are normalized so that they're unit vectors. So I want to normalize these by I want to say that it's V1 divided by the sum of V1, which is going to be the L1 norm of V1, right? They're normalized so the sum of the squares of the elements is equal to 1, but you want so the sum of the elements equal to 1. The second eigenvalue, once after you set gamma 1 equals to 1, so I could normalize the eigenvalues in different ways, and it's possible that different calculations are different ways of computing them are going to do this. But if you set the first eigenvalue to 1, then the second one is important, is it tells you how fast this converges. So this tells how fast it's going to converge. Okay, the smaller, the faster converges. Smaller gamma 2, faster convergence. Okay, yeah.
I'm sorry, why we're setting gamma 1 equal to 1?
It's actually the ratio of gamma 2 over gamma 1, but it's just easier to think about as like this ratio, right? So if you're not sure, look at gamma 2 over gamma 1, right? Then you can just do this. Okay, but often people just discuss it as the value of the second eigenvalue, as if gamma 1 has been, everything is divided through by gamma 1, so by lambda 1, sorry, lambda.
Sorry.
Yeah, so they'll talk about as if lambda 1 has been, all of them have been divided by lambda 1, so that one becomes 1. Okay, and so in the example graph, gamma 2 is equal to 0.875. Okay, so you might think, okay, this is pretty close to 1. But actually, it's sufficiently far that this will give a pretty fast convergence. Okay, so what's the right way of thinking about what this gamma 2 means? So think of anytime I'm in what the Eigen Decomposition is doing to you is it's a way of taking these state vectors and it's giving you a basis over them. And it's saying that because, if you remember, all the eigenvectors are going to be orthogonal to each other, I can take any state vector and I can write it as a linear combination of these eigenvectors. And in the limit, I want it to be just, in the limit, I just want to be all in the first eigenvector and none in the rest. Okay, and saying, what this is saying is every iteration, the part of the state distribution that is made up of the second eigenvector is being reduced by a factor of 0.87. Right? So I'm shrinking it by like 12% every step. And this is kind of an exponential kind of pushing it down. Every step, that part of the component that's describing its state in the second eigenvector is going down by 12%. Right? And so after 10 steps of going down by 12%, I'm going to be pretty small. Maybe less than 10% of the mass will be described, the probability distribution will be described by the second component, and everything else will be even smaller. So that means maybe 90% will be in the first component, so I'll have 90% of the probability distribution being roughly the same as the converged to state. Right? So this is a pretty fast enough rate of decay. If the second eigenvector is like 0.1, then this is a super fast rate of decay. I'm going to converge really fast. If it's like 0.99, then it's pretty slow. Okay? So this is, I would say this is going to already, this is going to be fast. Say gamma 2 equals 0.99. This is going to be slow. And gamma 2 equals 0.1. This is going to be super fast. Okay, so just a sense of scale. The 0.875 is already fast convergence. All right. One other thing I want to write up, just so you get a sense of it. is that this example graph, so in the example graph I showed in the first few slides, the Q star is going to be equal to 0.15, 0.15, oh sorry, 0.1, 0.15, 0.15, 0.15, or another one of those, 0.1, and 0.05. Okay? So it's kind of a little bit hard to predict what's going on. Down here, if you remember what the graph looked like, I have B, A, C, D, E, F, G, and I think H, like this. Okay, so H has the smallest. This has 0.05. I have the smallest probability of being out here. Meaning if stuff leaks out, it tends to stick here and then go over here. As likely to go over to this side as it is to go back in here. But if it's here, it's probably going to leak out. B has less probability than A or C. I think there's an edge between A and C as well. Right? It's less probability than A and C because if it's in B, it's going to leak out, but it might not come back. That's kind of conceptually. And so it's not a uniform distribution, the final state. And kind of in some sense, the nodes that have higher values, A, C, D, E, and F, C, D, E, and F, these are somehow more important. They're more connected to what's going on. These are higher values. They're somehow more important in some ways. Yeah?
But we will get that same Q star independent of which was the first state. Correct.
Yep. So you'll always get this Q star. This is the first, has to do with the first eigenvector of this this probability transition matrix. So it's independent of whatever the initial state, it will eventually converge to that. I won't know exactly where I am, but 50% of the time I will be in state D, and 10% of the time I'll be in state B, and so forth. If I'm writing this in the limit. Okay, so this is cool. We'll use this to analyze graphs. This is kind of giving you a sense of how to do this on Wednesday. Okay, this idea of looking at this Q star state. Okay, but to use it on graphs, you need to be a little bit more careful because of these ergodic conditions. You need to make sure those are satisfied, otherwise things go wrong, and some other sort of issue. We'll actually talk about this kind of fight between search engines and like spamming engines. That's kind of neat to think about. Okay. I want to spend the last 10 minutes talking about this Metropolis algorithm. So who's heard of the Metropolis algorithm before? Okay. Oh, good. Good. So a few people. Good. So it was invented in 1953 by Metropolis, Rosenbluth, Teller, and Teller. I believe both the Rosenbluths and the Tellers were husband and wife teams. But the guy with, I would say, the coolest name got it named after him, also first alphabetically. Does anyone know what they were working on in 1953?
Atomic bomb?
Yeah, so these were from the group of people studying the atomic bomb, and they were using this to understand kind of some states of the internal physics of what was going on. Right, that's right. So Teller was a big name in that, same Teller, and the Rosenbluths were involved in a lot of this as well. Okay, so what's going on here? So let me try and set this up. And so this is also used, or like relatives are used largely in Bayesian statistics as the way to kind of calculate the distribution over some kind of imagine, or some probability distribution that you set up. And so the idea is that you have a set of states V, and the V could be continuous, right? So often in Bayesian statistics, it'll be something like this. It could be real values in like d dimensions, or values between, for instance, you know, it could be some large universe where U is very big. It could be where something like RD or 0, 1 to the power D. It could be something like this, where it's something, it's going to be some very large state space. And the way you typically have access to it is that you can evaluate some weight for V as an element in uppercase V. Okay, so I can pick one state, and this is one state. It's often not thought of as a state. It's often thought of as an element of the state space, right? Instead of, it could be, this state space can be infinite dimensional in some ways. That would be okay as long as I can describe it and I can evaluate its weight. Okay, and I need the condition that the weight is going to be greater or equal than 0, and the sum, or in some cases it might be it could be that it's the integral of V in the state space, that this is going to be equal to 1. So the sum of the weights, or sorry, this is even worse, not equal to 1. These are going to be equal to some uppercase W. Okay? So I can evaluate it, like I can evaluate, given a condition, given a prior, I can evaluate the probability that, or the posterior of associated state in a probability distribution, or in this case, some physical model. I can calculate the energy associated with this physical model, and so weight will be related to the energy somehow. So often you'll set this equal, if this is in physics, it's often e to the negative, often e to the negative amount of the energy associated with V. So if there's a particular condition describing a physical system, I'll do e to the energy, maybe energy squared or something like that, and that will describe the state space, and that will describe the weight. Okay? And so I often don't know, you often don't know the value of W. Okay, so I don't know the value of W. Now, if the state space was small enough, I could compute this for all values of W, and I could add them up, and I would get W, but I don't know the value of W. Right? So I can look at two states, and I can say one is more likely than the other. The probability I want to be in that state, or the weight, like the probability of being in a certain energy configuration should be proportional to W, is what it will turn out. So I want to say the probability that V, of being in V is proportional to W of V, but I don't know the constant. I don't know if I need to take W of V and divide by 1,000,000 or 1,000. I don't know, so I can't get a sense of the probability of this. I can compare two things, but I don't know the overall probability. Okay. Okay, and so there are a lot of there are problems in physics where you got into situations like this, where somehow I could take the energy and I could get some weight, which I knew the probabilities were proportional to these weights, but I did know how to understand the state space. I did know how to understand the distribution of these objects. So what they did is they would run this, this random walk version of Markov Chain, which is called the Metropolis Algorithm. Okay, and so what you do is you start in some initial state, and usually, and in this case, I'm in this random walk version, so it's always exactly exactly one state, some configuration. I generate by some kernel, and think of this as often as like a Gaussian kernel. So so there's some Gaussian kernel. I'm generating something nearby in a probabilistic way. Right? So if I'm in a state V, I'm going to put a Gaussian distribution over here, and I'm going to draw a random element from this Gaussian distribution, and this will be U. Right? So some random element from this Gaussian distribution. Okay, if the weight in U is greater than the weight in V, that means it's more likely to go there. I'm always going to set this transition so the next state is U. If the probability is not greater, that means the weight was higher in the state I started in V, then I'm only going to sometimes go to set the next state as U with the ratio of the probabilities. Right? So if this is a lot, if U is a lot smaller than V, I'm probably not going to make that transition. But if it's close, then I'm, if this is 90% of V, the weight is 90%, then I'll make this step 90% of the time. Otherwise, I stay in the same spot. Okay? And I do this until it converged. And what converged means is kind of how do you detect if it's converged? This is still kind of a bit of an open question, but people kind of, there are some methods to try and figure this out in specialized cases. Okay? So I'm basically randomly walking around. Every step I pick a random neighbor in some way, and then I accept the state if the weight is higher, and I reject it with some probability if it's lower. And it turns out that the converge to, if I look at the distribution of these states in the limit, or more specifically, if I look at the limiting state, if I run this an infinitely long amount of time, and I look at the last state I'm in, that state is going to be equal to the, it's going to be in that state proportional to, so Vn as n goes to infinity, so the probability of Vn is going to be equal to the weight of Vn divided by uppercase W. Okay, so if I run this a really long time, I'm going to get essentially one random sample out of here. I don't get, what's typically done, typically what people do is they take V1 up to V1000, and then they V1001 up to V6000. And these are numbers which are pretty reasonable in here. They're going to take these and throw these away. This will be called the burn in phase. And then I'm going to take the second set, and I'm going to take the average. I'm going to treat this as if it's the real distribution. I'm going to treat this as if it's a distribution over the state space. And because it's continuous, even if it's not continuous, this often, I kind of take this as 5,000 states here. I count the number of times it appeared in a certain state, and I divide by 5,000. And that's the probability it's in it. If I want to integrate over a region of state space, I count the number of these which are in that region. And this is a typical way that it's used. Okay, and so this is kind of the main computational tool for doing Bayesian statistics. You would set up, instead of these weights, you'd set up some posterior distribution which you can evaluate. Right? But this was used in statistical physics widely to understand these unpredictable systems where they could only evaluate this weight value. And it would kind of a distribution of what's going to happen if I run this simulation. I'm going to do this. And so I only get this property in the limit, but this is typically how it's used. And there's some theory that says it's kind of okay, although it's an accepted enough thing that all of Bayesian statistics is built on. I'll just say that. All right, so I'll stop here. We'll talk about PageRank and how Markov chains are important for that on Wednesday.